Hello, thank you for inviting me to speak on this, the bicentenary of Joseph Aspdin's invention of Portland cement. It was on the 21st of October 1824 that Joseph Aspdin was granted his famous patent. But his invention didn't emerge from a vacuum. The search for a hydraulic binder suitable for the constructional needs of the age, widely available and economically priced, had been pursued in both theory and practice for several decades beforehand, and an understanding of the requisite geology and chemistry was gradually accumulated, albeit with many errors and digressions along the way. In a book published just 4 years after Aspdin, the author acknowledged this situation, and I shall quote: "The art of composing calcareous cements was confined, within the last few years, to the knowledge of a small number of facts, and to the observance of certain rules long since admitted into use without examination on the authority of Vitruvius and the architects who followed him. But the rules were almost always found to be at fault, and the facts, for want of correlativeness, were of little aid. It was necessary to work by guess in most instances, or to trust to obscure analogies for the success of the most important works. Every plan had its partisans. We shall leave it to the reader to decide whether such a chaos of opinions and opposing facts could or could not make up a science, a doctrine of calcareous cements." Now, I'm a librarian by profession, not a materials scientist, so indulge me if I glide glibly over the details of the chemistry, on which I'm not really equipped to speak, and approach our subject from an historical perspective, reviewing the literature and seeking to emphasise some underlying themes to aid an understanding of the broader development of binders. Regard this as a scene setting for the state of technology in 1824. The 18th century saw the start of an economic transformation that we today would call the Industrial Revolution, and it was accompanied by an increasing need for transport infrastructure to facilitate the movement of raw materials, of fuel and finished goods. It was also an age in which civil engineering appeared as a distinct discipline. It was in 1747 that the School of Bridges and Roads was founded in France, and in England, the engineer John Smeaton became the first to describe himself as a civil engineer. And 2024, the current year, is also the tercentenary of Smeaton's birth. The period was one of great achievement in civil engineering, but particularly in hydraulic engineering. We have much development of bridges and of harbours and docks and other maritime structures, but particularly characteristic, the development of the network of canals that typify that period. In order to fulfil these sort of projects, there was a demand for binders that would set rather than disperse in water. And we'll see examples of these engineering projects that helped propel the development of binders as we go through this talk. Rising demand challenged the capacity of traditional sources of supply, however, particularly Pozzolana from Italy and Greece, and caused inflationary pressure on prices. Moreover, the distance from the Mediterranean, where the sources of material tended to be, to the north of Europe, where industry was developing, caused further constrictions in supply and led to a search for new sources, alternative materials, or artificial substitutes. Traditionally, in Europe, binders were based on lime, quick lime made from the burning of limestone or chalk, and then slaked and allowed to harden by exposure to air. In the Renaissance period, in the late 15th century and the 16th century, the ancient classical use of Pozzolana was rediscovered through the publication of the works of Vitruvius, Pliny the Elder, and other classical writers who promoted the use of Pozzolana, the volcanic ash from Pozzuoli in southern Italy. They also referred to the artificial substitute of brick dust or crushed ground tiles. And then, as the time went on into the 17th century, the greater use of Dutch terrace or Dutch terrace as it was known at the time. We might call it trass today. A volcanic tuff from the Eifel region of Germany that was sold through the Netherlands, hence its name. By the middle of the 18th century, where our story is to start, the use of hydraulic limes through one method or another was becoming well established. It was not only were the improvements through the use of trass or pozzolana undertaken, but also in certain areas some limes were known to be naturally hydraulic. I can take an example from this period. George Semple, an Irish engineer who built the Essex Bridge in Dublin, for instance, recorded in slightly later life his search for suitable limes, and refers to finding it in the area around Warrington in northwest England. Similarly, in France, we have the example of Prannoy, who was the founder of the School of Roads and Bridges, and therefore his work can probably be taken as an exemplar of best practice at that time. He similarly built bridges. He similarly wrote in retrospect about them, and the bridge at Neuilly, for instance, across the Seine, used a white mortar from Vernon lime, and then for the foundations where hydraulic lime was required, he refers to the use of an artificial pozzolana from ground tiles, but not brick. The state of the art, insofar as it appeared in print at the time, would be through the works of Belidor, a prolific writer of books on architecture and engineering, who wrote several of relevance to our subject, but particularly the Architecture Hydraulique, which came out over a period of 16 years in multiple volumes, and are known to have been read by both Semple and Smeaton at the time. He wrote much of great practical use, including, as you'll see from the pictures on the screen, production methods. He also wrote about the use of ash from the ironworks in Tournai in what is now Belgium as an artificial pozzolana. But he promulgated the erroneous belief that the harder the source of lime, the purer it would be, the better it would be. So he would argue for marble as a source, and at the other end of the spectrum, chalk would be the least usable. And he was his thinking in this line was widely accepted and certainly followed in print by writers throughout the rest of the century and into the early 19th century. Much of the work involved in identifying limes was carried on piecemeal in the middle 18th century. Certain amount was hearsay or happenstance, but there's very little in the way of systematic testing. One example that contradicts that, however, is that of John Smeaton, who we've already mentioned, and he was invited in 1756 to replace the Eddystone lighthouse, which had been destroyed by storms. The Eddystone lighthouse is just off the coast of southwest England in a very sea-swept location, and his role was to build the replacement of a more durable material. He proposed granite blocks and needed to identify the most appropriate mortar for binding the two together, the blocks. And in doing so, he tested numerous samples to discover what would be best for his purpose. And in doing so, he made a number of important discoveries. I won't go through the experiments in detail, but pick out in his own words a couple of key conclusions. One is that hardness underwater did not depend on the hardness of the stone, thereby contradicting the work of Belidor. The fitness of lime for water building depended on the amount and composition of clay impurity. There we go. It's clay that's the important aspect in conferring hydraulicity to the lime. He tested 300 different types of limestone and found the most effective was the Aberthorpe Blue Lias, and there was a percentage of 11.2% clay. He also looked at the use of pozzolana, confirmed that Italian pozzolana was perhaps the optimum material of its type, although he did experiment with what he describes here slightly obscurely as a ferruginous substance of a similar nature. This is known to historians of the time as minion. It's not a term that's used today. Smeaton was a key figure in the unfolding of cements and the discovery of cements in this period. He was the starting point, I would suggest, and his role was widely recognised in retrospect. So writers in the 19th century, for instance, look back upon Smeaton as being a key person in the development. The quotation on screen is from Wilhelm Michaelis in the 1860s, but there are others of very similar verbosity. However, Smeaton's work was not widely known, at least not through the printed word, because his work wasn't published until a year before his death. And in 1791, this enormous folio, it must be, I don't know, 2.5 feet tall. It's a big book. This was published in 1791 and made his experiments and his conclusions known to a much wider audience. We know that it was available to Joseph Aspdin, for instance, in later decades. However, although it was not, his work was not well known through the published word, and therefore not known in Europe, it was increasingly known in Britain through a network of personal contacts and professional dealings. So his assistants, such as William Jessup, but there were others, involved in canal building in the years immediately following the Eddystone Lighthouse, and his counterparts also in canal building, such as James Brindley, all experimented with the use of different naturally hydronic limes from Barrow, for instance, and from Sutton in Lancashire. And the canals that you see listed on the screen are all those that involved some form of improvement to the lime. Canals were an important nexus for the use of mortar, but it wasn't the only one. In architecture too, there was a great requirement for stucco, which is a form of decorative render to A, waterproof a building, but B, make it look more prestigious than the basic brick course behind it. There was a brief period in the 1770s where oil cements were developed. These were where the medium was oil rather than the lime, and so the oil would be a medium, and then fillers would be put into it. Needless to say, the material didn't work very well. It tended to fail within a matter of years, and so consequently this whole area of activity disappeared. But for a while it was popular, and the most prominent writer of this period in this country, in Britain, was Bryan Higgins, an Irishman who'd studied in Belgium and then practiced in London. And he spent a 5-year period experimenting with calcareous cements. He didn't use the clay, the oil, but developed a use of ground lime and bone ash as the basic constituents. His patent enshrining the optimum formula was published in 1779, and then he wrote a book about it. This is an important book. It's the first in English, and indeed the last for the next 30 years. He was at pains to quote the work of Vitruvius in his writing, and he was by no means alone in this. Here on the screen we can see 3 examples. These are all French writers, and they all refer to the Greeks and the Romans, or les Romains, les Anciens. The example of Rome was quite in vogue at that period. There have been tremendous archaeological discoveries in Italy, particularly in Rome and also in Pompeii, and neoclassical architecture was fashionable. So the example of Rome was quoted by most involved in this line of work. The Swiss historian Salvatore Apria has identified 2 strands of research from this period on for the rest of the century. The development of new sources or alternatives to Pozzolana, and the scientific study hydraulic lime. And we take those in turn and look at Pozzolana. Most activity was in France, and we see a string of scientists, geologists, chemists, naturalists finding alternative forms of volcanic ash that could be used as a pozzolana. And in the case of Chaptal, the fourth point down, he started to experiment with artificial pozzolana, calcining clays and schists that he'd found in Languedoc in 1787. France wasn't alone. There were other countries involved in this search too. Perhaps most prominent was Sweden, where we can cite the works of Kronstadt and de Bagger. Also in the Netherlands, Adriaan de Boys, he investigated the clays of the canal network in Amsterdam and used his research to develop an alternative form of binder. And then also in Silesia, in Germany, now Poland, we have the rather splendidly named Adolf Trigot von Gersdorf, who experimented with calcining local basalt. The other line of inquiry, the scientific study of lime, was really prompted by the discoveries of Joseph Black, British physicist, who was the first to describe the lime cycle. And that was just a year before Smeaton's work on hydraulic limes. But without Smeaton's written work, some of the investigation went off in some dead ends, blind alleys, call them what you will. Bergman in Sweden analysed a naturally hydraulic lime and discovered it had 4% manganese oxide, and he quoted this as well. He considered this to be the important constituent for the hydraulicity. The Frenchman de Morveau accepted these conclusions and combined materials in exactly the same proportions, and of course found that they formed a hydraulic lime, so perpetuating that idea. And it wasn't dispelled really until the Swiss geologist de Saussure found, when discovering the rocks of Chamonix, that it was actually clay. There was no manganese in the hydraulic limes that he found, but there was clay, and he came to similar conclusions to Smeaton, but independently some years later. In Britain, the search for a hydraulic lime was overtaken by the discovery of a natural cement. This would be a material that didn't change volume on combination with water and would set hard within maybe 10 minutes. And this was a material that was discovered supposedly by accident by the Reverend Joseph Parker, who found that cement stones, or septaria, found on the beach around the estuary of the River Thames, if heated and then ground down, would form a naturally hydraulic cement. This discovery, supposedly accidental, was also very shortly after Smeaton's work was published, so we might presuppose some prompting to his investigations. Anyway, by 1796, he had lodged a patent, having had it tested by the eminent engineer Thomas Telford. He called it Roman cement, very much in keeping with the times. It's a name that's been poo-pooed in later years, but was fashionable at the time. It wasn't the only source of natural cement, the River Thames. I mean, there are other parts of England and mainly England, not so much in Scotland, were found to be suitable sources of material of cement, but also in France, in Boulogne, then by the 1818, should I say, in America, where it was used for the Erie Canal, and then increasingly throughout Europe, France, Germany, the Austro-Hungarian Empire, and so on. The search in Europe, however, was given a boost by the economic consequences of the Napoleonic Wars, particularly with the blockade and the continental system that characterised the later period of the war. Supplies were in short supply and prices were increasing. So there was quite a a motive to find alternative sources. And so we find here the harbour at Cherbourg, the commander, a name called Lapeyre, experimented with materials from the coast, calcining them and mixing them in varying combinations. These were tested by a French commission, which rather hopefully thought it might improve by prolonged submersion. So not particularly successful experiments. Much more important was the work of Vitalis at Rouen, who was a professor of chemistry, and investigating two types of limestone, discovered that clay was the key distinction in making it hydraulic. The most important figure in this period of French investigation was Vicat, who was an engineer tasked with the job of building a bridge across the Dordogne at Souillac. And as you'll see from the picture, it has multiple piers set in the water, so he needed a hydraulic lime. As it wasn't available through the normal channels, he decided he would have a go at developing an artificial version. And without going into his experiments, he was very successful and developed an artificial hydraulic lime, which was reported in his in the press in 1817, and then his own book in 1818. And the French Academy granted, made it available without patent to French industry. His achievements were many and varied, and the bullet points on screen are from Laurent Iseret, who was writing at the time of Vicat's bicentenary 2018. I'll highlight the one that is in bolder type here. The manufacture of hydraulic limes was no longer dependent on local geology. He'd found a way to replicate nature in artifice. It would be churlish to ignore the role of his counterpart from Berlin, Johann Friedrich John, who was professor in experimented in multiple subjects in Berlin, multiple chemistry-based initiatives. He responded to a Dutch Academy of Science competition and undertook research in 1815 to 17 into artificial hydraulic lime. And he won that particular competition in the same year as Vicat's work was published. And he published his own work a year later. Vicat's work was mixed fortunes in the years immediately after his publication. Most prominent, I suppose, would be the work of Maurice St. Leger, who set up a factory to produce the material. On the other hand, General Trout, when building or repairing the fortress at Verdun, couldn't achieve the same results as Vicat had when he tried to replicate the experiments, and decided that Pozzolana was a more reliable way to proceed than trying to make a hydraulic lime. In Britain, we have a series of patents reflecting a great interest in artificial cements after the patent for natural cement had lapsed in 1810. There's a number of fairly short-lived patents, people entering into production and then falling by the wayside. James Frost was more successful than most, patriotically naming his British cement, albeit on the basis of advice from Vicat himself in France. But the one we remember, one more, William Lockwood, in 1823 had gone into production himself. He previously was a sales agent for Roman cement, but decided that he would make one of his own and experiment with different sources of raw material from Swansea and from Leicestershire, and entered into production in his own right. And significantly, a year before Aspdin, he was describing himself in the trade directories at the time as Portland and Roman cement manufacturer. But the name Portland was locked in and protected by Aspdin's patent of the following year. And so the name from that point is protected, and the material itself represented a new step in the progress. Not that Portland cement hasn't changed since, it clearly has, but it was identifiably a material, the forerunner of what we have today. So In summary, we can say there are a number of underlying themes to what I've said: the demands of economic expansion, the requirements of hydraulic engineering, and the need for affordable sources of supply prompted investigation. The ongoing inspiration of classical Rome shaped its direction and led to a gradual accretion of knowledge, although there were plenty of wrong turns along the way, such as the manganese misconception. The Napoleonic Wars acted as a catalyst to research. We might point out also that there were many discoveries made by chance and in many cases independently. But to try and overcome the independence of study, there was also considerable effort in publication. We can see that particularly in France, where there were numerous published treatises. I've listed some of the authors that I've touched on in this talk on the book cover to your left. And on the right, we can see the British equivalent, which wasn't treatises, it was patents. They're short legal documents rather than more scholarly works. The work of Dr. Higgins, as we can see in 1837, it was remarkable that the publication of Dr. Higgins, since his publication, no English work on the subject has yet appeared. That was written by J.T. Smith in 1837, who was the English translator of Vicat's work. Translation became an important step in overcoming the barriers to knowledge. We can see that Belidor was read by Smeaton and Semple, Vicat read Smeaton, Swedish research appears in French books, but in this country, in the United Kingdom, there was, after the works of Loriot, there was really no work appearing in English until Vicat's work was translated in 1937. And then in 1838, Charles Paisley made available to an English-speaking audience a much wider canon of French research. So given that vacuum, given that lack of published material in the 1820s, it's perhaps all the more impressive that Aspdin, a provincial builder from Leeds, all the more impressive that he should have come up with the patent for Portland cement and the cause of our celebrations this year. I'd be very pleased to answer any questions. Thank you.